welcome back. And we're going to continue our discussion on phase changes, and particularly we're going to relate the idea of phase change back to vapor pressure, which relates back to boiling point. And there is this classical equation that's used in thermodynamics to figure out the change in vapor pressure, which can be attributed to the change in the heat of vaporizing a liquid from liquid to gas. Okay, and that is Clausius-Clapeyron equation. And this is the equation. You do not have to remember this equation. Now, if you remember, I used a different value of gas constant. Okay, this is just another one of those. Again, so you don't have to remember. And as we do more problems, I will tell you where to use which gas constant. Okay, but sometimes I might give you a specific gas constant in the question itself, so you do not have to have that confusion. Now, you do not have to remember this equation nor this value. Now, let's take a quick look at the equation before we actually work out a problem, because working out the problem itself is not all that difficult. With that said, P corresponds to pressure in general, R is our gas constant, T is your temperature, and T must be expressed in Kelvin. Okay, not degrees Celsius. Even if it's in degrees Celsius, you got to convert it to Kelvin. Okay, and then T is obviously the temperature, right? So what is this equation really trying to tell you is, if you know the pressure, okay, at a particular temperature, so P1 is the pressure at temperature T1. Okay, you would see this relationship even more obvious as we begin to discuss gas laws. Okay, the pressure inside a chamber when it's heated depends entirely on the amount of heat made, right? So if you're going to put ice, that pressure is going to be different than when you're really heating it up with a red hot flame. Okay, similarly, pressure 2 is the pressure at temperature 2, right? So if you know these two information, and you know the gas constant and the temperature at which something is carried out, then you can most likely calculate the delta H vaporization, right? So let's go now look at the question, right? Now, as I already said, delta H vaporization is actually the amount of heat, or the change in heat, right? Amount of heat required, right? Required to transform 1 mole of a liquid. It could be any liquid, any substance, 1 mole of a liquid to gas. With that said, we have benzene. The normal boiling point of benzene is 80.1 degrees Celsius, and the enthalpy of vaporization is 30.8 kilojoules per mole. What is the boiling point of free benzene in Denver, where atmospheric pressure is this, and the pressure at normal boiling point? We know that STP is 1 atm, but again, pressure can also be expressed in other units. So this is the pressure, right? Now actually let's go look at the problem. All right, so what and all the information that we know in the equation that we, oh, actually the T is not here, sorry about that. Okay, accidentally typed it twice. Okay, so this doesn't have the T. So if this is, if whatever condition that we're talking about, this 80 degree and then this 1 atm, maybe that's say Lexington or Kansas or anywhere, right? But we want to know what temperature benzene would boil at. Now again, this question would help you answer, why would liquid boil faster in Lexington or would boil faster in Denver? Okay, Maybe this question would directly answer that question. So let's say P1 is our normal temperature, which is 101.3 kilopascal. Okay, and the corresponding temperature is 80.1 degrees Celsius, right? Keep in mind, this has to be converted to Kelvin. We'll come back to this. And the pressure in Denver is P2, which is 83.4 kilopascals. And we are asked to find, so this is our T1. Okay, this right here is our T1. We are asked to find T2. We are given the delta H vaporization as 30.8 kilojoules per mole. Okay, so now we got to do a few basic cleaning up work before we can actually solve this problem. First aspect is we got to convert this to Kelvin, right? Because if you notice, the gas constant, which is 8.314, there's two other conversions that we have to do. One is, this is in joules and this is in kilojoules. Either we should convert the joules to kilojoules or kilojoules to joules. Okay, I always convert just the joules to kilojoules to make things easier for me. But let's make sure we convert this to Kelvin. And how do we go from degree Celsius to degree Kelvin? We take whatever the given temperature, which is 80.1, and we add that to 273. Okay, so 273 plus 80.1, which is 353.1 Kelvin. So that's 353.1 Kelvin, right? And then if we convert this to kilojoules, that means we divide 8.314 by 1,000. So to go from joules to kilojoules, we divide this by 1,000, which would give us 0.008314 kilojoules per mole Kelvin. Now we are ready to tackle the problem. So natural log of P1 is 101.3 kilopascal, P2 is 83.4 kilopascal, so the units cancel out, equals enthalpy of vaporization is 30.8, R is 0.008314, 1 over T2 is what we are asked to find, minus 1 over 353.1 Kelvin, right? All right, very good. So let's go ahead and solve this. So 101.3 divided by 83.4, and then we take the natural log of the answer. So this side of this is 0.1944 equals 30.8 over 0.008314, 1 over T2 minus 353.1 Kelvin. Now you have to do some math here. So multiply this by 0.008314, divide by 30.8. So you get, I'm going to do this last piece of conversion math in red. So when I multiply this and divide by this number, I get 0.000524. That's equals 1 over T2 minus 1 over 353.1, right? So let's do 1 over 353.1, which will give us minus 0.0028, okay, equals 1 over T2. We can just move it to this side and add it to our other number, 0.00524. So basically 1 over T2 equals 0.00288. So T2 equals 1 over 0.00288, which equals to 346.6 Kelvin. So do you think benzene would boil faster in Denver, or would it boil faster in any other place of your choice that I asked you to pick, say Lexington? Where do you think benzene would boil faster? So do you think water would boil faster in Lexington, or would it boil faster in Kentucky or in Denver? Okay, so this is how you tackle a Clausius-Clapeyron equation. Now I did walk through this problem very clear, so please make sure to rewatch this video and make sure how I solve this problem, right? I have only one more video on this topic of intermolecular forces, so stay tuned.